Hello, and welcome to A Tale of Two Stages. This grew out of a mystery, or what I thought was a mystery, having to do with second stages. And let's see if I can frame this appropriately. So I'm going to talk about two different rockets. I'm going to talk about Falcon 9 on the Starlink 28 mission. And the second stage, mass, was about 128 tons. The thrust was about 100 tons. So thrust divided by mass, thrust to mass ratio of about 0.78. There's a different rocket, an Atlas V Centaur on the NROL 101 mission. Mass 27 tons, thrust 11,000. Thrust 11 tons. So thrust to mass 0.41. And okay, what's the mystery? It's like, how do these work? Don't you need to have that ratio be higher than 1? Why don't they just fall out of the sky? So that's the mystery that I'm going to talk about in this video. I want to say at the front that I heavily used data from flightclub.io, which is just a tremendous resource if you want to dig deep into the details. And it shows you just a ridiculous amount of information. So many thanks for the information there. To start, I want to talk about orbit for a little bit, because the whole goal of doing these missions is to put something into orbit. So orbit, here we have the Earth, here we have our rocket 200 kilometers above the Earth, which is kind of the lowest part that I'd say is orbit. At that altitude, gravity will pull down at about 9.2 meters per second squared. And what that means is if it was just stationary at that altitude, 1 second would go by and we would move 9.2 meters closer. Is that right? No, it's actually not quite right, but it's close enough. So let's think of what happens a second later. If we moved forward a second, if we moved directly forward, we would be a little farther away from Earth. And our goal is to be right at Earth, right at 200 kilometers. So remember, it's going to be pulling us down. It turns out that if we move forward 7,784 meters and move down 9.2 meters, we will be still at 200 kilometers away from the Earth. So, in other words, the Earth is curving away at the same speed that we are being attracted to the Earth. So, that is really what it means to be in orbit. We're moving forward fast enough that the Earth attracts the satellite, but the Earth curves away at the same time, and they balance out. So what does this mean? Well, it means the orbital velocity at 200 kilometers is 7,784 meters per second. Now, if we were farther away from the Earth, gravity would be less, and what would that mean? Well, that would mean that our velocity would be lower. So as we go farther away, our orbital velocity goes down, which might be a little counterintuitive, but that's the way the physics work. And speaking of physics, there's some more detailed physics I need to talk about. It's kind of going to be the real root of how I analyze and explain what's going on. So here we have a rocket sometime after launch. We're going to measure the angle it has with the ground. So 90 degrees would be straight up, and here it's probably 60 degrees. If it's pointing more to the side, it's a lower number. And then we have acceleration going forward, whatever direction the rocket is pointed. And this arrow is what's called a vector, and it really indicates two things. The direction it's pointing is the direction of the acceleration, and the length of it, or the size of it, is the magnitude, or the amount of the acceleration. So vectors are pretty common in physics, and they're going to be very useful when we talk about what's going on. In addition, there's a velocity vector, and perhaps kind of surprisingly, the velocity vector is not necessarily in the same direction as the acceleration vector. It might be more to the side, or it might be more vertical. So initially that seems a little weird, but if we think about what Falcon 9 does, on some of its launches, the first stage, after it separates, actually turns around and relights its engines so that it's going back in the direction. So its acceleration vector is almost against, in the other direction of the velocity vector. And then finally, there's gravity, and gravity always pulls straight down. Now there's something that's not very convenient about these sort of vectors, because one of the things I'm going to care about is gravity pulling us down more than we are accelerating up? But it turns out that we can decompose or break these vectors into separate components. So we can take that velocity vector, here's the horizontal part of the velocity, and here's the vertical part of the velocity. And we can do that same thing with the acceleration. And notice that the vertical part of acceleration is now directly in opposition with the gravity, which is always, of course, vertical. So that's the physics. Let's talk about the first mission. So I have the Falcon 9 sitting on the launch pad. Here are some stats. Time is 0, altitude 0, velocity is 0. Gravity at the Earth's surface is about 9.8 meters per second squared. Acceleration when we light the engines is 13.2 meters per second squared. And of course, we're pointing straight up. Now I'm going to draw what in physics is called a free body diagram. So this is the rocket, and I'm going to draw in the forces that are acting on it. Now, for the sake of this discussion, I'm going to ignore any drag, so you won't see that anywhere. So we're accelerating vertically at 13.2 meters per second squared. Gravity is pulling us back at 9.8 meters per second squared. And if we add those together, what do we find? We find we are accelerating upwards at 3.4 meters per second squared. And a few things to note. First of all, we had to have a thrust to weight ratio more than 1 here. We have to be accelerating up more than gravity pulls us down, or we don't get off the launch pad. The other thing to note is that 3.4 meters per second squared really is not that much acceleration. And that is why when rockets are first launched, they don't move very quickly. So we're going to move ahead a little. We're at 75 seconds. We're up to 12 kilometers. We're moving about 460 meters per second, so really not very fast. Our acceleration is now up to 19.6 meters per second. And the reason it's gone up is we've burned off fuel for 75 seconds, so our rocket is much lighter. The angle of the rocket to the ground is now 50 degrees. So let's do the diagram. There we are, 50 degrees. There's our acceleration vector. Gravity is pulling us down. We will convert the vector. So what we see is our vertical acceleration is still more than gravity. So that means our vertical velocity is going to be growing. And we have quite a bit of horizontal velocity. I mean, quite a bit of horizontal acceleration. And this makes a lot of sense. Remember, to get into orbit, we have to get nearly 8,000 meters per second of speed sideways. So we need to be building that up. We'll jump again a little bit more to 150 seconds, 58 kilometers up to 2,200 meters per second. Gravity is a little bit less, our acceleration is all the way up to 35.3 meters per second squared. We've burned almost all the fuel in the first stage, and our angle is down to 32. This is approximately MECO, or main engine cutoff. So this is right before we are going to stage and switch over to the second stage. So here's our diagram. Here's the acceleration vector, 32 degrees, gravity 9.8, and we can see that we have a lot of horizontal and we have a lot of vertical, but so we will still be gaining speed vertically right before we shut off these engines. But there's now another factor that we need to take into account. So at 58 kilometers, our orbital velocity would be 7,870 meters per second. We know our velocity is 2,230 meters per second. We know that the angle of the velocity is 26 degrees. So what we can do, we can break that vector apart and we can see we are moving sideways, horizontally, at 2,000 meters per second. Okay, we'll compare that to the orbital velocity and we will determine that we have 26% of the orbital velocity at this point. Okay, that is actually very interesting. You remember when I was talking about orbit, when we are all the way in orbit, the acceleration of gravity was counteracted by the curvature of the Earth. Here we're about 26% of that velocity. What that means is some of the gravity is counteracted by that curvature, by that horizontal motion. So we'll recast that. The curvature is now giving us the equivalent of 2.5 meters per second. It's counteracting that much gravity, so we still have 7.1 meters per second. So that means once we've started moving sideways a bunch, we get more vertical acceleration than we kind of think we would. Now we're going to switch over to the second stage. Okay? Everything has stayed the same except for the acceleration. So we had 9 big engines on the first stage. We have 1 engine on the second stage. So what does that mean? Well, our acceleration is much, much lower, 7.6 meters per second. We see that these arrows are much smaller. The important one to note is the vertical acceleration is 4.4 meters per second squared, while gravity is pulling us down at 7.1 meters per second squared. What does that mean? Well, that means our vertical velocity is going to be decreasing. Now, I can finish this diagram on the left side. We can tell that at this point we have a positive vertical velocity of nearly 1,000 meters per second. And if you remember, our goal with orbit is to be in orbit to have our horizontal velocity be orbital velocity and our vertical velocity to be essentially 0. So this makes a lot of sense. We want to actually be slowing down in vertical velocity so that when we get to the orbit we want, we are actually stopped. So that's where we are. We've switched to the second stage. We'll move to 300 seconds, 149 kilometers. Our speed is up to 3,080 meters per second. We really didn't speed up that much. Remember that the second stage accelerates a lot slower. Our acceleration now is up to 10.8. Our angle is much, much farther over. We're pointing more horizontally. So do the diagram again. 10 meters per second squared going horizontal, 4 meters per second squared going vertical. And we'll do the other diagram. We're now at 5 degrees. So we've lost, we're now pointing much flatter. Our vertical is now down to 270 meters per second, our vertical speed. Horizontal, about 3,070, so we're up to 39% of orbital velocity. So that's fast enough. We now are up to 3.7 meters per second squared, canceled out by the curve of the Earth, and gravity is still 5.7. So we're still slowing down, but you notice we still have 270 meters per second. So we still need to slow down a little more to get to 0 vertical velocity, or something close to that. And then finally, 540 seconds in, 167 kilometers. We're going much faster, 7,590 meters per second. And we're accelerating at 38.3 meters per second squared. So we've used up almost all of our fuel. So we're accelerating quite quickly. And the angle is down to 6 meters. I mean 6 degrees. This is right before second engine cutoff. So we're almost done getting into orbit. There's a diagram. So 38 meters per second squared sideways. So right before this, we've been gaining speed really quickly and a little bit vertically. And we'll do the other diagram. We're almost flat now. There's very little vertical velocity. Just barely, 66 meters per second, 97% of orbital velocity. And what does that mean? Well, that means almost all of gravity is counteracted by the curvature of the Earth. We just have a little bit slowing us down. And you can see, in fact, that right at this point, our vertical acceleration is much greater than gravity. So we're actually getting faster going vertically again. It may be there's some noise in the numbers here. It may be because this is a Starlink mission and we aren't actually intending to stop at 167 kilometers. We need to be coasting up higher. So that is the state for what happened on this Falcon 9 launch. And you notice I really didn't talk about thrust to weight ratio. The interesting part is the first stage's job is to get us moving upwards pretty significantly, a fair bit of vertical velocity. And then the second stage's job is to get us moving sideways and to keep enough of that vertical velocity so that we get to the altitude that we want. So let's move on to the second scenario. Here we have the Atlas V Centaur on NROL 101. This is the Atlas V launching in what they call the 5-3-1 configuration. What that means is the fairing on the top is 5 meters. You notice it's a big fairing. Satellite is inside of that. There are 3 solid rocket boosters. We can see 2 of the white boosters on this side. There's another one around on the other side. And there's a single engine on the second stage. So that's what the 5-3-1 means. Start here. I didn't start on the launch pad because I didn't think it was very interesting. So we're going to start at the time when the solid rocket boosters are just finishing their burns. So 113 seconds, 46 kilometers, 1,250 meters per second, acceleration of 17.5 meters per second squared. The angle is still 65 degrees. So we're still thrusting upwards pretty significantly. We really haven't started leaning over very much. Here's the diagram. What do we see? Well, we're building up a little bit of horizontal velocity, but we are really trying to thrust vertically a lot. Much later, 260 seconds, we hit main engine cutoff. So 180 kilometers, 5,400 meters per second. That's pretty fast. And we're accelerating at nearly 40 meters per second at 4 degrees. So we're, okay, so let's do the diagram. What do we see? We see a lot of horizontal velocity, a lot of horizontal acceleration. So we're really trying to build up horizontal velocity at this point. We only have a little bit of vertical acceleration. So let's look at this compared to orbital. We'll do some vectors. We're at 11 degrees on our velocity. That means 5,300 meters per second horizontal, or 69% of orbital velocity. So what does that mean? 6.4 meters per second squared of gravity is counteracted by the curvature of the Earth. That leaves us only 2.9. So at this point, we're slowing down a little bit, but we're not slowing down a lot, at least in the vertical direction. But that doesn't matter that much. We have over 1,000 meters per second of vertical acceleration. So at this point, we'll switch, we'll stage, and we're going to light the engine on the second stage. And everything stays the same except for the acceleration. And it goes from nearly 40 meters per second all the way down to 4 meters per second squared. So the RL-10 engine on the Centaur is not very powerful. It's very reliable, it's very efficient, but it doesn't put out a lot of thrust. And we remember the thrust-to-weight ratio was 0.4. So let's draw the diagram, a very short arrow here. And we see 3.9 meters per second to the side and only 0.3 meters per second vertically. So everything else is the same. What we notice is now we have much more acceleration back towards the Earth because we lost a lot of vertical acceleration because the stage is so much weaker. The engine is so much weaker. So what does that mean? We're going to be slowing down vertically relatively quickly. But once again, remember the whole goal here is to reach the orbit we want with no vertical velocity. So this is about the time it makes sense we would want to be slowing down here. We'll jump ahead to second engine cutoff, 725 seconds, altitude of 307 kilometers, 7,700 meters per second, and accelerating all the way up to 7.9 meters per second squared. So even when all the fuel is burned, the Centaur just can't accelerate that quickly. So we'll do the diagram. We're going pretty much at orbital velocity and pretty much all horizontal. So there's really no vertical. I've shown that almost all gravity is counteracted by the curve, and there's a little bit left pulling us down. There's probably some noise in the figures here. We are pretty much in orbit at this point. So that is what it looked like for this launch with the Atlas V Centaur. So now I want to compare and contrast them and show you two different views of these two launches side by side. And first we're going to do a little bit of a pop quiz. So here is two charts showing velocity versus time. Which one of them was the Falcon 9 launch and which one is the Atlas V Centaur launch? So, okay, it's really pretty obvious which of these is which. So what we can tell on the Falcon 9, we know Falcon 9, the first stage booster comes back and lands, and we can see in the left chart, the booster continues and it comes back and lands. And we know for the Atlas V that it has solid rocket boosters and it has a first stage and a second stage. So we see in the right chart, the solid rocket boosters come off at some point and the first stage comes off. So you can just kind of tell by what they look at. So that's really not why I wanted to look at this chart. I wanted to look mostly at the timing. So what we notice is over here on the left, we see that the first stage of the Falcon 9 is finished at about 150 seconds and maybe 2,200, 2,300 meters per second. And then we have the second stage does a whole lot of work to go from 2,200 all the way up to orbital velocity. If we look at the Atlas V Centaur, it's very different. The first stage goes all the way to 53 or 5,500 meters per second. So it creates much, much more velocity than the first stage. And then the second stage, the Centaur, is really kind of weak. It takes a long time to generate this small amount of additional velocity. So we see two different launchers, two different kind of philosophies. And the reason they're so different is really kind of a different design approach or a different goal on the two teams. So the Atlas V Centaur, the reason they use the Centaur is a stage that has been around forever. It's incredibly reliable and it's quite efficient because of it uses hydrogen, liquid oxygen in the second stage. So it's a very good stage, but it's not really great at giving you a lot of delta V. So what that meant is, once you decided you were going to use Centaur, you needed a big, beefy first stage. And in fact, not only do you need a big, beefy first stage, you may need to augment it with solid rocket boosters for specific payloads. So that is why the Atlas V has such a big, beefy stage, and that is why it stages at a high velocity and quite a bit later. Now, flipping over to the Falcon 9, SpaceX knew when they started with the Falcon 9 that they were going to try to reuse the first stage. And they wanted to make that as easy as possible for them. What that meant was they needed to have the first stage to second stage transition happen at a fairly low velocity. So they essentially built a big, beefy second stage, and that could generate a lot of velocity, or a lot of delta V, and then built a first stage that could do the rest. And that's really important for recovery and reuse, because the big challenge for reusing the first stage is making it back into the atmosphere through re-entry successfully without burning up. That's much, much, much easier if your first stage is traveling 2,200 meters per second than if it's traveling well over 5,000 meters per second. This is one of the reasons why we don't see reuse on the Atlas V. It's probably not possible to bring that whole first stage back through the atmosphere without it burning up. There's another advantage in this. If you have your staging pretty early, it means that if you want to land on a drone ship out in the ocean, your drone ship is relatively closer. If you think of how close the SpaceX ones are, which was maybe 400 to 1,000 kilometers, something in that range. If you think the Atlas Centaur ones would have to be much, much, much farther out, much later in the flight. And that would just be much harder logistically, and it would be more expensive. So that is why SpaceX chose to design this sort of way, the big, beefy second stage. Now, there's probably another reason why they chose this. When the Atlas V was designed, they had the Centaur and everything worked, so it didn't make a lot of sense to put a lot of money into a new second stage. SpaceX knew they had to build a new second stage from scratch, and they didn't have an engine for it. And it turned out that if they took one of the Merlin engines from the first stage and made a vacuum engine, they ended up with a big, beefy engine. And that gave them the second stage working the way they wanted it. It's also true that to get this first stage, which is a little less beefy, they still needed to use 9 Merlin engines. And 9 engines at the time seemed a little ridiculous. And if they wanted to have a beefier first stage, they either would have had to accept less payload, or they would have had to use even more engines. And that, of course, would be crazy. Well, of course, they're doing it in Starship. But at the time, that was a nice trade-off for them. So I hope this was interesting. I think it's very, very interesting to see 2 very different approaches. They're both 2-stage rockets. I guess you can call the Atlas V 2.5 stages if you include the solid rocket boosters. But they have very different philosophies for how they get into orbit. Now, in case you didn't catch it, to go back to the mystery I talked about at the beginning, there's really no mystery because thrust to mass or thrust to weight doesn't really make sense for second stages, because second stages start their job when they're already moving horizontally quite a bit. And you notice the Falcon 9 second stage, it starts pretty early. We aren't getting much benefit from going horizontal, so it needs to be pretty beefy. It needs actually a pretty high thrust to weight ratio. Atlas Centaur, the Centaur stage, We're already going very fast horizontally, so it doesn't need to be as beefy. It doesn't need that high thrust to weight. Thank you for your attention. I hope it was enjoyable. Please subscribe.